So as we mentioned, or as I mentioned, we are going to revisit hypothesis testing in Chapter 9. We are not going to do all of Chapter 9. We're only going to do the first 3 sections. And we're going to be talking in this chapter about testing the difference between two samples. And specifically, we're going to test the difference between two means, two sample means. We're not going to cover proportions, or we haven't done variances in any of the chapters. So we're only going to be doing means. Section 9.1 will be like kind of an introduction, and then 9.2 will be means with a known sigma, with a known population standard deviation, and then section 9.3 will be mean with only the sample standard deviation, not having the sigma. So in section 9.1, as I said, we're going to kind of learn the concepts. So the concept of testing the difference between the parameter of two samples. And remember, a parameter is just the population, some measurement in the population. If it's in the sample, it's called a statistic. If it's in a population, it's called a parameter. And in our case, we've done population mean. The other chapters we did proportion. And then you can also do confidence intervals and hypothesis testing on standard deviation, but we have not done those. But a parameter is just some measurement of the population. We're also going to talk about how to do hypothesis statements for testing the difference between two sample means, because it's a little bit different than doing the hypothesis statements that we did in Chapter 8. So when we're talking about this type of hypothesis testing, rather than having a new sample that we're comparing to prior information, researchers sometimes want to know if a parameter from two samples shows the samples are from two different populations that are similar, or if they are from populations that are so distinct that we would consider them as different populations. So, for instance, this image kind of helps. So, if we get done with our hypothesis testing and we find that the two samples are so similar, are pretty similar, then we say, oh, well, those two samples were out of the same population. Let me draw it even a little bit different way. So here's our population. And if we find at the end of our hypothesis test that the two samples are very similar, which means we would not reject the claim, then we're saying sample 1 and sample 2 are actually just samples out of the same population. Whereas if we find that the samples are quite a bit different at a certain level, we'll have our alpha levels again, then instead of thinking that they're from the same population, we would actually consider that they were from two distinct populations. And that's why they're so different, is that sample 1 is from population 1 and sample 2 is from population 2, that they're not from the same population, that they are so different that they must be from two different populations. So when conducting the hypothesis test, if the test statistic is small, we conclude the difference is not significant and we lack evidence to reject that they're equal. On the other hand, if the test statistic is large, the difference is large enough that we conclude that it's not due to chance and that the underlying parameters are unequal samples from two distinct populations. So again, the first situation is where it is small and that means that they're probably from the same population, but if we have a large test statistic, then we're going to end up with the assumption that they're from two different populations. Okay, so let's see what that looks like. I'm going to start with, what do the hypothesis statements look like for these types of hypothesis tests? When we start our null hypothesis, you'll notice with these three examples, with these three types, we don't have any numbers. So remember before we would always say, you know, the null hypothesis is that the mean is 50, and then the alternative hypothesis, we might have the mean is less than 50, greater than 50, not equal to 50. Okay, but we always had this number here. In these types, since we're not comparing to a prior study, since we're just comparing two samples to each other, we're not going to have a number anymore. Okay, so instead of having a number there, we're going to compare them to each other. We're going to say mean 1 equals mean 2 as our null hypothesis. You notice that's the same in all three of these. And then just like before, once we get the two things written down here, the alternative hypothesis has the same two things. It's just before it was mu and a number. Now it's mu1 and mu2. So we're going to write down mu1 and mu2 again, and then we're going to write down what we're trying to compare. Are we trying to say that they're not equal? Or are we trying to say that mu1 is bigger than mu2? That the average of sample 1 is bigger than the average of sample 2? Or are we trying to say that the sample average, or the sample average of the first sample is smaller than the sample average of the second? And remember, mu, we're actually trying to determine if the populations are significantly different, but smaller, greater, or not equal to each other, to one sample or one population to the other sample or population. So when we do these are the four types, literally the only three, I said four, but I meant three, the only three types of hypothesis statements that we can have. We start with mu1 equals mu2, and then our choices are either mu1 not equal to mu2, mu1 less than mu2, and mu1 greater than mu2. All right, let's look at just some examples of just doing the hypothesis statement. Just like we did before, here in 9.1, we're just going to try to do the setup for the hypothesis statement, and then in 9.2, we'll actually do the full hypothesis test. So a company has two stores and wants to know if the mean daily sales of the stores are different. This is a two-tailed test. So two stores, they're going to find the mean daily sales for the two stores. So you're going to have mean 1 and mean 2. And they just want to know if the two stores are different. So in this case, not equals. Are they different? But there's no number in here. There's just the comparison of the two means. Or say a school district would like to know if North High School has a higher mean on the standardized state exams than South High School. Let North High School be sample 1, then this would be a right tail test. So if North High School is sample 1, we're looking to see if South has a higher mean than North. That's our claim or our charge. Not that they're equal, but that South has got a higher average than North. Or we could have one where, like this case, a meteorologist wants to know if there's been less snow on average this winter in Colorado, in the Colorado mountains, than in the mountains of Canada's British Columbia. So if we consider Colorado as sample 1, we're saying Colorado snow is less than Canada or BC. We say BC for British Columbia. So Colorado's snowfall is less than that of British Columbia. And again, there's no numbers in here, so there's literally just 3 ways that you can write the hypothesis statements for these because we don't have the numbers. We just have mu1 and mu2. Okay, so let's see an example of one of these. So here in section 9.2, we're going to be testing the difference between two means using the z-test. Now that indicates to us that the population standard deviation is known. Okay, so that's the population standard deviation. And so because we know the sigma, we can use z-test. Now, one of the things about this type of hypothesis test is the formula looks very intimidating. But if you look at the formula, well, I'm getting ahead of myself. When we do these types of tests, both samples must be random. The 2 samples also have to be independent of each other. And for doing a z-test, we have to know the standard deviations of both populations. If for some reason you knew the standard deviation of one population but not the other, then we'd have to treat it as if we didn't know either one of them. And then we like the sample sizes to be 30 or more. But if they're not, if we have a smaller sample, then we want the populations to be normally distributed or approximately normally distributed. And we're just going to assume for all our examples that all samples less than 30 are approximately normally distributed. So you don't have to really worry about that, but just know that is a criteria. So now to the formula. This formula looks kind of intimidating, but think back to the formula that we had before. So before we had z equals x bar minus mu over sigma over square root of n. Now what's different here is because we have 2 samples, we basically have to double every one of those variables. So instead of x bar, we have x bar 1 minus x bar 2. But it's just the sample average from one minus the sample average of the other. And then we're going to subtract the population average minus the population average for the 2 populations. Then we're going to divide, and we just have to do this division of the sigma and the sample size twice. Now, in order to keep there from being 2 different square roots on the bottom, they combine them all underneath the square root, and then they square the sigmas. So we have sigma squared and sigma squared for the first sample and the second sample. And because they square it, then we can put everything underneath the square root sign. Okay, so this isn't as bad as it looks. I know it looks kind of awful. Let's give it a shot. Not every one of your homework problems will be like this, but anything on the exam is going to be set up with a table like this. Now, I think there are a couple on your homework where they don't have the table, but and you'll have to pick it out of the paragraph. But when I give it on the exam, I like to give the table because there's just so much info in these with the 2 different samples. So, a researcher hypothesizes that the average number of different math classes that community colleges offer in science is greater than the average number for math. So I think there's more variety of science classes than for math classes. So the researcher took 2 random samples of 50 colleges and shows that there's 8.6 science classes and 7.9 math classes on average. Assume that the standard deviation of the number of classes is 3.3 for both science and math. Can we say at alpha equals 0.10? There's enough evidence. So most of this information is already filled out in the table. You'll notice here it says, that X bar 1 is 8.6 and X bar 2 is 7.9. So it is up here in the paragraph, 8.6 and 7.9, but it's also filled in the table, so it's a little easier to see. Same thing with the population standard deviation. It has sigma sub 1 and sigma sub 2. It said that our population standard deviation is 3.3 for both of them. So we have sigma sub 1 is 3.3 and sigma sub 2 is 3.3. And then it also says that 2 random samples of 50 colleges. So N sub 1 and N sub 2 are both 50. Now, you will see in some cases where they, like in this case, will take like the science and the math classes from the same 50 colleges. But in all honesty, these are supposed to be 2 completely random samples. So you really should not be taking the same 50 colleges for the math as you do for the science. It should be get 50 random colleges, look at their science classes, then get another set of 50 colleges and look at their math classes. Now, you could you could randomly pick the same college possibly in each sample, but it shouldn't be all the same 50 colleges. It should be a completely different random sample of 50 colleges for each of the samples. All right, so moving on, our hypothesis statement. Science is our sub 1, is our first sample. So science is like sample 1. And math is sample 2. And what we're trying to check is that science is greater than, let me erase some of this stuff up here that I've circled so we can see it a little bit better. They want to know, is the number of classes in science greater than the average number for math? So science is 1 and math is 2 for the sample numbers. So our hypothesis statement, we're always going to start these with the status quo or the assumption that mean 1 equals mean 2, that the two are the same. But the claim by this researcher is that mean 1 is actually larger than mean 2, that science is larger than math. So our second step, the same as always, is we're going to find a critical value or values. So we need to know, just the same as in the past, what's the alpha, how many tails is it, and what kind of a test is it? Well, our alpha level is 0.10. It is a one-tail test because we're only looking at greater than. So it's a one-tail test, a right tail. And then it is going to be a z-test because we have the population standard deviation. We have sigmas. And so we can do a z-test. We don't have to do a t-test with the degrees of freedom and all that because we have the better information of the population standard deviation. So we're going to go to our chart as always, alpha 0.10, right tail, z-test. Okay, so here's our one tail, 0.10, and it's a z-test, so we're going to go all the way to the bottom. And that's our smallest z-value that we've used of 1.28. So now we're ready for our test value, which is our formula. And if you forgive me, I'm not going to write that whole formula down. We'll just refer to it as we put numbers in. So we need the x bar 1 minus the x bar 2. X bar 1 is 8.6. X bar 2 is 7.9. And then an interesting thing happens here with the next part. Mu1 and mu2 were assumed to be the same. Remember, our hypothesis statement was that mu1 and mu2 will equal. Well, if they're the same, then mu1 minus mu2 is going to be 0. We don't even know the values for them, but we know it's going to be 0 because we assumed they were the same, and anything minus itself is going to be 0. Then on the bottom, we need sigma 1 squared. So sigma 1 is 3.3. And we need to square that. Then we're going to divide that by the sample size, which is 50. So 3.3 and 50. Then we're going to add that to the sigma 2 squared, but sigma 2 is the same as sigma 1, so that's 3.3 again. And then our sample size is the same for both samples. These numbers don't have to be the same, but for this problem they happen to be. Okay, so the top is 0.7, and then we're going to get our answer for the bottom and divide the 0.7 by that answer. So we've got 3.3, whoops, let's get our square root here first. Square root of 3.3 squared divided by 50 plus 3.3 squared divided by 50 again. It's all underneath the square root bar. Hit enter, I get this 0.66. And then I'm going to take the number that I had on top, that's 0.7, and I'm going to divide it by that answer. And I get 1.06 approximately. So how does that compare? What's our decision going to be? Well, 1.66 is below 1.28. So it's in the clear, it's not in the shaded region, in the rejection region, not in the dark. And so we are going to not reject because we're not in the critical region. Do not reject because we are not in the critical region. 1.6 is below the necessary 1.28. And so in conclusion, there is not enough evidence to support the claim that there are more science classes than math classes. In other words, we can go on the assumption that the average number of science classes and the average number of math classes at community colleges is about the same. Okay, so let's look at our next example. We have 40 men and 45 women. So this one's a little different right off the bat. We have different size samples, but that's okay. The formula can handle that. Found that the average daily intake for men was 3,653 and for women was 3,482. Now, you might be tempted at this point to think, oh, the men was higher than the women, so I'm going to do a greater than. But we haven't gotten to what they want us to test yet, so let's hold off on that. So right now, all we know is for our hypothesis statement that we are comparing the means of two samples. And so we know the null hypothesis is that mean 1, mu1 equals mu2. Assume that the population standard deviation from previous studies is 324 for men and 287 for women. Okay, again, we've got different population standard deviations, but they are both given. We have the population standard deviation for both. At alpha equals 0.05, can we conclude the difference in average sodium intake is significant? Difference. So they're not asking us to say the men are higher. They're asking us to see, is there a difference between the two groups? Are they not equal to each other? Okay, so now for step 2, we are going to do our critical value or values. And we need to know our alpha. We need to know what the tail is, and we need to know what type of test we're doing. Well, the test, we have sigmas. If we have sigmas, we can do a z-test. We don't just have the S's, we don't just have the sample standard deviations, we have the stronger information of the population standard deviations, so we can do a z-test. And we know it is, we're looking at a difference, and so it is a two-tail. We want to know whether either the men are higher or the women are higher, if there's a difference between the two. And so we're interested in higher up or down on our test. So this is a two-tail, and we know it's alpha equals 0.05. So we're going to go to our chart and we're going to look at alpha 0.05 two-tail z-test. Two-tail, alpha 0.05, and it's a z-test, so we're going to go all the way to the bottom. And we're going to get our 1.96 from our 0. So 1.96, and it's a two-tailed test, so we're going to have our negative 1.96 and our positive 1.96. Okay, so now we're ready again for our formula. Try to get both of these on the screen at the same time. So when we go to plug in, we need z equals x bar 1 minus x bar 2, which is our 3,653 minus our 3,482 from up in our chart. Then again, we had the assumption that the mu1 and the mu2 were the same. So that mu1 minus mu2 being the same means that if we subtracted them, we would get 0. And then on the bottom, we're going to have everything under the square root bar. And we have sigma 1 squared and sigma 2 squared on the top. So sigma 1 squared is 324 squared. And then sigma 2 squared is 287 squared. So we just plugged in these sigmas. And then our n's are different. We have 40 for the men and 45 for the women. Okay, so the top, calculate that real quick, is 3653 minus 3482 and hold on, I put something in wrong. 3653 minus 3482, and that gets us 171 for the top. And then we're going to calculate the bottom and divide by that answer. So we've got 365, oh, we already did that, square root of 324 squared divided by 40 plus 287 squared divided by 45. And that gets us the 66.7 So we're going to do 171 divided by that answer, which gets us about 2.56, which does fall high enough to be in the critical region, in the rejection region. Okay, it would be up in this area, it would be above the 1.96. And so, because we're in the critical region, we're in the rejection region, we are going to reject the null hypothesis because the test value is in the critical region and there is enough evidence to support the claim that there's a difference between the mean sodium intake of men and the mean sodium intake of women. So again, we would say there is a statistically significant difference between their sodium intake, and so we're going to reject the idea that they're the same, and we are fairly certain that they're different, that they are not the same. Now we can't change and say men is higher than women because that's not what we tested. We tested that there was a difference. So we have enough evidence to say that there is a difference between the intake between the men and the women, but we didn't test that the men were higher. So we can't, in our conclusion, change our conclusion from what we were testing. Remember, when you do these, a lot of times you would do that null hypothesis. Almost always, you would do the null hypothesis and the alternative hypothesis before you would ever do the samples. So we're given everything all at once, but the researcher would choose their hypothesis statement and their critical values before they would go and do their sample. Okay, so the difference of population means with a fixed difference is a little bit different type of comparison between the two samples. It's got some similarities, but it's a little different. Now, when I'm testing you, I will not give you a problem like this with the fixed difference. However, there's a couple in your homework for section 9.2 rather. There's a couple in your homework for section 9.2. So, it'd be good if we did an example of one. So sometimes instead of assuming two populations have the same parameter, or in our case mean, research has found that the two populations have a fixed difference between them. So they might say the difference in heights between two different groups of people might be, fixed at a known difference of 3 inches, or there might be a known difference between the average test scores of students in 2 different states, or something like that. And so instead of checking to see if they're the same or different, you're checking to see if that difference might be different or smaller or larger than the known difference. And when that happens, if we say that that known difference is K, let's say, then these are the 3 options for our hypothesis statement. We're going to start with always that the difference is K. That's the known difference that we're given. And the researcher could either say, is that difference not K? Or is that difference smaller than the given K? Or is that difference bigger than the given K? But we're always looking at a difference for the null hypothesis. Oh, these ones have the second hypothesis wrong. These should all be 1s, of course. Get a little fixing on that. So null hypothesis, alternative hypothesis, H sub 0, H sub 1. So let's look at this with an example. And in this example, a gardener bought 2 varieties of tomatoes. Okay, so these are something that is known, two varieties that are have been grown a lot, measured a lot, and maybe on the package or somewhere in an advertisement, as it states here, that the medium variety and the large variety were advertised to be 2.5 inches difference in diameter. And then both of them have a standard deviation of 0.3 inches. So the population standard deviation of both is 0.3 inches. But this gardener, she believes that the plants she has grown are closer in size than 2.5 inches. So she's not seeing as much of a difference between her large variety and her medium variety as she thinks that the stated difference is. So she's going to sample her harvest. She has a 0.1 significance level. Can it be concluded that the difference between the varieties is less than 2.5 inches? So our hypothesis statement, when we're talking about a fixed difference, we're going to go, null hypothesis is that mu1 minus mu2 has that fixed difference. So in this case, 2.5 inches. Then the alternative hypothesis in this case is that the difference between them isn't as much as, is less than the stated difference, that they're closer together than they are advertised to be. The difference between the varieties is less than 2.5 inches. So then we're ready for our critical value. So now we're going to look for that critical value, or values, and then just as always, we're going to need to know our alpha. We're going to need to know what kind of test, and we're going to need to know how many tails. So our alpha is stated to be 0.10. We can see from the table that we have the sigmas that was stated as the 0.3 inches. So we know we're doing a z-test because we have the sigma. And we know in this case, we're only interested in if the difference is less. So we're only interested in the left hand, the left tail of our normal curve. So it is a one tail left tail. So we're going to go to our chart and we're going to do a alpha 0.10 left tail z-test. Alpha 0.10 left tail z-test. Okay, so one tail 0.10 and then all the way to the bottom for a z-test. And that gets us the 2.33 value. Oh, I looked at something wrong. Alpha 0.10, one tail. Oh, I looked at 0.01 instead of 0.10. Let me back up. Okay, alpha 0.10, not 0.01. Z-test all the way to the bottom. All right, so we have 1.28. And because it's on the left side, because it's to the left side of 0, that's going to be negative 1.28. So now we're ready for our formula. And really the only difference in doing the formula with these fixed difference problems is our difference is not going to be 0. We're going to have a fixed difference. So our sigma 1 minus, or our alpha, our x bar 1 and our x bar 2 are 8.9 and 6.6. 8.9 minus 6.6. And then we don't have to compute this. We know from our hypothesis statement and from the statement above that we think the difference between them is 2.5. So the difference between mu1 and mu2 from our hypothesis statement is 2.5. So that's this portion of the formula. So that's 2.5. And then underneath we have square root of sigma 1 squared, which is sigma 1 and sigma 2 are both 0.3. So 0.3 squared and 0.3 squared. So that's this part right here. And then we're going to put in the sample sizes. So the sample size for the large variety was 19. And for the second sample, which was the medium variety, was 22. So let's compute the top really quick. 8.9 minus 6.6 minus 2.5. So we're getting negative 0.2 for that. And then on the bottom, we're going to get that answer and divide that negative 0.2. So pull the calculator up for that one. Square root of 0.3 squared divided by 19 plus 0.3 squared divided by 22. And then we're going to take negative 0.2 divided by that answer. And we get approximately negative 2.12. Actually, I think it rounds to 1.3. 128. So yes, negative 2.13. So how does that fall? If we compare that to our critical region, negative 2.13 would be down here below our negative 1.28. So we'll look at their nice, pretty picture. We've got negative 1.23 down here in the shaded area. So we do reject the null hypothesis because we are in the critical region. There is a statistically significant smaller difference between the two varieties than you would expect just from a random sample difference. So there is enough evidence to support the claim that the difference between the tomato varieties is less than 2.5. Now I'm going to point out on this one because I think this one's worded better than our last one was. So this is worded more along the lines of what a researcher would know. So as I was mentioning, whenever you're doing hypothesis test, usually the researcher will know these first two steps before they do any sampling. They will have their hypothesis statement. They will know what critical values they want in their z-test, that they're doing a z-test or a t-test, and what tail it is. They'll know that before they do their samples. And then after they do their samples, and they can check their test value and make their decision. But researchers don't know their sample information before they start the hypothesis test. So hopefully that makes it make a little bit more sense why, like up here, the researcher, we already know what the sample got for the men and the women. But the researcher, when they would have done this, they would have said, I wonder if there's a difference, and gotten their hypothesis statement. Then they would have decided what alpha level and that they wanted it to be two-tail and so on. And then they would have taken their sample. So they wouldn't have known their sample average and their of the two samples before they started to know that, well, maybe I should do a mu1 greater than mu2. They wouldn't have known that because they wouldn't have taken their samples yet. Okay. So now we are done with section 9.2 and we are ready to finish up chapter 9 with 9.3. Remember, in chapter 9 we're only doing the means. We're not going to do proportion. It's not required. They just want us to introduce this type of testing, but we don't have to do the various types. So we're only going to do mean with the sigma and mean without the sigma. And then we're going to be done with chapter 9. So now we're going to be testing the difference between two means of independent samples using the t-test. So using the t-test, that means we don't know the sigmas. We only know the s's, which means we're going to use the t-test. Whenever we have only s, we follow with the t, and that means we're going to be doing degrees of freedom. All right, so the things that we need, we still need both samples to be random. We still need them to be independent of each other. And we still need that if either sample size is less than 30, for the population to be normally distributed or approximately normally distributed. All right, and our formula is the same, except our z is now a t and our sigmas are now s's. Oh, and I wanted to point out, I knew there was this was somewhere, I was trying to find it. So to do the t-test, if you don't end up with the samples being the same size, then you use the smallest n. So for instance, if you had n1 was 72 and n2 was 55, you would use this for your degrees of freedom. Your degrees of freedom would be 54. So you're always going to you're going to err on the side of caution and use the information from the sample that's not as good, which would be the smaller sample, to compute your degrees of freedom. Some books, this is one of those things that does have some different beliefs as to what should be done, and I have seen books where they do the average between the two samples, but our book errs on the side of caution and uses the smallest sample. So if you run into one in your homework where the samples aren't the same size and you need to do a t-test, use the smaller sample for your degrees of freedom. All right, so let's see our last example here for chapter 9. It says we have random samples of 10 neurosurgeons and 10 orthopedic surgeons. The neurosurgeons had an average monthly income of $28,436 and a standard deviation of 1657. Orthopedic surgeons had a $27,164 with a standard deviation of 1853. Can we conclude, alpha 0.05, that there's a difference in the means of the two populations? Okay, so in this case, it says the samples found us this standard deviation. And then the sample got us this standard deviation. So these are not sigmas, they're s's. And if you're in doubt with these types of problems, you can look in the table because it says it's an s. So our hypothesis statement, we're back to assuming that they're the same because there's no stated difference. So our null hypothesis is that mean 1 and mean 2, mu1 and mu2 equal each other. Our alternative statement, alternative hypothesis, is that there is a difference in the means. So just mean 1 does not equal mean 2. Mu1 does not equal mu2. Now we're going to look at critical values, and we need our alpha, we need to know what test we're doing, and we need to know the tail. Since it's a not equals, that's a two-tail test. My normal curve to look decent. There we go. Still not great, but better. Okay, so it's two-tail. So we care about both ends of our test. So two-tail. Our alpha is 0.05. And in this case, since we have S's, we're going to be doing a t-test. And because we're doing a t-test, we'll need to know our degrees of freedom, which in this case, both samples are 10. So we use that, 10 minus 1, and get a degrees of freedom of 9. So alpha 0.05, t-test with degrees of freedom 9, two-tail test. That's what we're going to be looking up on the chart. Two tails, 0.05, degrees of freedom 9, and so we're only going to come down to this number instead of going all the way down to the bottom. So 2.262, and because it's two-tail, also negative 2.262. So now we're ready for our formula, which again is almost identical to the other formula, just with T's and S's. So we have x bar 1 minus x bar 2, which is 28,436 minus 27,164. Then we're going to divide by the square root. Oh, and then our mu's are 0 because we had the assumption that mu1 equals mu2. Our S's are this 1657 and 1853, so we're going to do 1657 squared on top of that one and 1853 squared on top of the other one. And then our n's are both 10. And so our top number, 28,436 minus 27,164 is 1272. And we're going to divide that by the answer. And for one last time in this chapter, we'll pop up our calculator. We have square root of 1657 squared divided by 10 plus 1853 squared divided by 10, all under that square root bar, gets us that 786, and we're going to take 1272 divided by that answer. And that comes out to be approximately 1.622. So it's 1.6. Got a little different than what the slide says. Let's double check this. So we have 28,436 minus 27,164. Okay, so that number's the same. And then on the bottom we have square root of 1657 squared divided by 10 plus 1853 squared divided by 10. And then we're going to take 1272 divided by that answer. I'm getting 1.618, which isn't going to change our final answer, but I did not get 1.622. I got 1.618 after computing it twice. Okay. So now 1.618 is not high enough to be in the rejection region. This is the middle. 1.618 would be down in this area, which would not be high enough to be in the shaded region. And so we do not reject the null hypothesis because the test value is not in the critical region. 1.622 is down in this area, which is not in the shaded area. And so there is not enough evidence to support the claim that there's a difference between the mean monthly income of orthopedic surgeons and neurosurgeons. Their incomes are close enough together from our samples that we did not find that there was a statistically significant difference. And so we have to go with the assumption, with the null hypothesis assumption, that their incomes are the same. All right, good luck on your Chapter 9 homework. And generally on the final exam for Chapter 9, I usually just put one problem on. So there's usually just one problem from Chapter 9 on the final. And it will be given with a table. So you'll be able to recognize it more easily because it'll be in that table form. All right, good luck with your homework and have a great rest of your day.